Hi, I'm Mr. Drach. Today we're going to be talking about energy diagrams. Now, what an energy diagram looks like is what you're seeing right now. Over on the axes over here is our energy. Usually it's in kilojoules. Doesn't necessarily have to be, but energy would be over there, and then time is on the bottom. We could have a very fast reaction, like an explosion, or we could have a very slow reaction, like rusting. Okay. Now, if you notice our reaction, it's A plus B goes to C. A and B are over here. Those are our reactants. And basically, we have to go over this hill to get to part C. And those are our products. All right. Now, the activation energy is how much energy it takes to get to the top of the hill. If we don't have enough energy to get to the top of the hill, our reaction will not proceed. Okay, we call that the activation energy. Sometimes you'll see that AE for short. Other times you'll even see EA for short. Okay, either way, it's called the activation energy, and that's the energy we need to get over the hill to get a reaction to occur. One analogy might be a skateboarder. They want to roll down this hill to get to part C. What they have to do first is get to the top of the hill. They only make it partway to the top of the hill, no reaction. Okay, they have to make it all the way to the top, and then we get a reaction. The same goes for a match. Okay, if we only partially strike a match, nothing happens. We again have to get to the top of the hill to get a reaction to occur. Okay, now what we call the top of the hill, again, this part right here, we have a couple of names for it. Sometimes we call it the activated complex, or also the transition state. Okay, but both of those places, sorry for the crooked lines here, both of those are at the top of the hill. Okay, so all the way up there. Okay, now here are a few questions we could ask you about energy diagrams. We could ask you, what are the energy of the reactants? Well, our reactants are over here. So I would call that about 220 kilojoules. And then I could also ask, what are the energy of the products? The products are way over here. And I would call that about 80 kilojoules. We could also ask, what is the activation energy of the forward reaction? Again, that is the energy to get to the top of the hill. In this case, we're going from about 220 up to, I don't know, 340. So we would just take the difference then. We get about 120 kilojoules. So that would be my activation energy. I could also ask, what is the energy of the forward reaction? And what I mean there is, how much do I start with? How much do I end with? So that would be about from here to there. I'm going to say I'm going to end with about 60 kilojoules. Okay, so the difference would be 220 down to actually more like 80 kilojoules. In that case, it would be about 140 kilojoules for our forward reaction to occur. And again, that would be from here down to, well, made that a little low, about to here actually. Okay. Now, if you notice that heat during the reaction, by the way, that is what delta H means. It's a change in heat or change in enthalpy. If you notice, the heat went down. It went from 220 down to 80. Okay, and that's going to be in the negative direction. Okay, and so I'm actually going to put a negative 140 kilojoules. Okay, and really the actual correct way to do that would be 80 minus 220, and that would give us our 140. Okay, now since it's a negative heat, since heat is released, that is an exothermic reaction, and I know that because it's negative, and I know because it dropped lower than it started. And so that is definitely going to be an exothermic reaction. Now, compare that to the next one. The next one is an endothermic reaction, okay? Because we end up a little higher than where we started, okay? Now, the energy of the reactants would be here, again, A plus B. I'm going to put that at about 60 kilojoules. Where I end up is up here. That's about, I don't know, 210 kilojoules. The activation energy of the forward reaction. Again, that's how high I have to climb up the hill to get my reaction to occur. In this case, we're going from about 60 to 360. So my activation energy is about 300 kilojoules. Okay. Energy of my forward reaction. I'm starting at about 60. I'm ending at about, I don't know, 200 or so. And again, I kind of mess that up. I should do 200 minus 60. So, in this case, I have positive 140 kilojoules. Okay? In this case, it is a positive heat that is an endothermic reaction. Okay? So again, notice the difference here. There's exothermic, drops lower. Here's endothermic, ends up higher. Okay? Now, we also talk about what a catalyst does in a energy diagram. Okay? And a catalyst is not a list of cows. Anyone get that joke? Catalyst? Catalyst? Okay. What a catalyst actually does is it lowers the hill. Okay? So with the catalyst, our hill would actually be kind of like this. Okay? Again, this is with our catalyst. Now, all it does is it lowers the hill so that now it's easier for our reaction to occur. I don't have to get as high on the hill as I used to. Okay? Now, what does that change? Okay, it only changes one thing on the screen. The only thing it changes is our activation energy. Again, that's how much I need to get to the top of the hill. If you notice, now I don't need to get as high as I was before. Everything else stays the same. Okay, my energy of my products and reactants are the same. The change in heat is the same, but now I just have a lower pathway to get from my reactants to my products. Okay, instead of going over the really big hill, now I'm just going over this small hill to get there. Okay, different pathway. Okay, we can also have reversible reactions. Instead of just having that one arrow, we would have a double arrow. Okay, now when we have that, we mean the reaction can go this way and this way. Okay, so when I ask the energy of reactants and products, same thing. The activation energy of the forward reaction, I could say it's from here to here. That's my activation energy. But here's the thing. My activation energy of the reverse reaction, going backwards, is now way higher. Okay, this is my activation energy of the reverse reaction. Okay, because again, that's how high I would have to climb that hill going backwards. All right. The other thing that kind of changes is my heat change. Okay, the heat change here is about 220 down to about 60 or so. So my heat change is 140 kilojoules. For the forward reaction, it would be negative 140. But for the reverse reaction, it would actually be a positive 140 kilojoules. One way is going to be, in a forward reaction, that's going to be exothermic. In a reverse reaction, that's endothermic. Okay? So it really depends kind of what we're talking about for a reversible reaction going kind of back and forth. So make sure you know which way you're going. Just to remind you, this is the forward going this way. And then if I go the other way, that's my reverse. That just about does it. You may or may not want to watch this last slide, depending on if you got here or not. But sometimes we actually have a couple of hills, and we call those multi-step reactions. So we actually have two steps. We have one step and another one right here. We actually have a couple of activation energies. We have two activated complexes, or two different transition states. And we also have something called an intermediate, which would take place right here. Okay. Well, that just about does it for energy diagrams. I will see you in class a little bit later. Mr. Drach signing off.